we move on to crystal field splitting. This is something very interesting and it is very important for the idea of magnetism. The difference in behavior of rare earth and transition metal is that 4f shells responsible for paramagnetism or ferromagnetism or antiferromagnetism in rare earth ions that lie deep inside the ions. That means 4f shells are covered by 5s and 5p states, while 3d orbitals that are responsible in transition metals, 3d transition metals, they are kind of outermost shell, because if you consider ions of the transition metals, the s electrons are given away. The positive ions of transition metals have s electrons given away. So 3d becomes the outermost shell in that case, and therefore it has a strong dependence on the crystal field, on how the magnetic properties behave. Let us see in pictures to understand how these things work. If we consider isolated atom, then it does not have any, it is not in a crystal, so therefore there is no question of a crystal field in that kind of an atom. So it has many degenerate orbitals. For example, if there are 3 p orbitals, all those p orbitals are degenerate. Let us consider 3d orbitals, those are most interesting in our case. There are 5 3d orbitals, all those d orbitals are degenerate. That means all those are at equal energy level. However, if we consider an atom in a crystal, the situation becomes different. The atom is coordinated by few other atoms, and depending on the crystal, the coordination style of the coordination differs. If we consider high symmetric crystal like cubic crystals, mostly there are 2 different kinds of coordinations. One is octahedral, that forms an octahedra after the octahedron after the coordination. It has 6 neighbors, and the other one is tetrahedral. It forms a tetrahedron, keeping the ion of interest, atom of interest at the center of the tetrahedron with 4 neighbors. So here is one example of octahedral coordination. The center atom, the pink one, that is our 3d transition metal ion of interest, and these white atoms are the coordinating atoms. So you can see that there are 6 white atoms. This makes an octahedron, keeping the transition metal atom at the center. And if we look at the energies of the 3d orbitals here, we can see that xy, yz and zx, they have lower and equal energy. So these are 3-fold degenerate. On the other hand, z square and x square minus y square, they have higher energy, and these 2 are also degenerate. So these 3 orbitals are called T2g orbitals, these 2 orbitals are called EG orbitals. T2g are lower in energy, EG are higher in energy. Why is it so? Because if you look at the orbital shapes, xy, yz and zx, they have this kind of a shape. They do not point towards x axis or y axis or z axis. They are lying in between x and y axis, and these ligands, these directions are x axis, y axis and z axis. So these 3 orbitals are not pointing towards any atom in the surrounding. Therefore, they have a lower energy, because the Coulomb interaction is not that effective in this. However, if we consider EG orbitals, these orbitals are pointing along this, and these orbitals z square, they are pointing along these atoms. Therefore, Coulomb interaction is stronger, and because of that Coulomb repulsion, they have higher energy in case of octahedral coordination. Now, if we look at a tetrahedral coordination, this is the picture. Here the situation completely reverses. We have Eg with lower energy and T2g with higher energy, but the splitting is still Eg and T2g, and the splitting could be different if the crystal field is different. So, there are many different possibilities for crystal fields in many different crystals. This is for higher symmetric crystals, cubic crystals, that this kind of crystal fields are realized. Also, apart from cubic crystals, these crystal fields are realized. So, we will now see what is the consequence of this kind of crystal field splitting of the otherwise degenerate states on magnetism. So, they have quite serious implication on magnetism. If we consider an octahedral crystal field, T2g is lower and Eg is higher in energy, and if we consider very strong crystal field, that is this gap between T2g and Eg is pretty large, then we will have upspin and downspin electrons. So, if we have 5 electrons in the d shell, we will have 2 of the T2g orbitals occupied by upspin and downspin electrons, that is fully occupied, and 1 is partially occupied, while Eg will be completely empty. And this will give us how much of spin? This will give us 0 from here, 0 from here, and half from here. So, this is a low spin configuration for this kind of a system, because we have a very large crystal field splitting. As opposed to that, if we consider a weak crystal field, a small crystal field splitting, then we can have all the orbitals, all the 5 orbitals that we can see here partially occupied. And if we have all the 5 orbitals partially occupied, clearly it leads to a high spin configuration, where the magnetic moment coming from this atom would be much larger. Therefore, you can see that the crystal field effect has quite strong consequence on the magnetic properties of a material. And also Hund's coupling strength matters. Hund's coupling strength tells you the energy difference that should appear between doubly occupied and partially, so upspin and downspin electron. The splitting of upspin and downspin electron comes from the Hund's coupling strength. So, an interplay between crystal field strength and Hund's coupling strength that suggests whether a low spin configuration would be realized or a high spin configuration would be realized. And in many different kind of crystal fields with many different number of electrons in the 3D orbitals, the consequences could be very different. So, this is about crystal field effect in crystals.